welcome. Thanks for coming to this talk so late in the day and so late in the week. Man, it's been quite a week here. Tons of great sessions. I hope you guys got to see a bunch of them. I didn't get to see hardly any. But we're going to wrap up the sessions today with the treatment of some of the hyperconverged solutions that we're doing here at Red Hat. We'll start with a few level-setting introduction slides. As you can see, there are several people up here on stage. Actually, one of them's sitting down, Steve over here. We're going to cover three different unique solutions that are based on hyperconverged innovations. So OpenStack with Ceph, traditional virtualization with Gluster storage, and container-native persistence. So I'm joined here on stage by Tushar Katarki out of the System Design Engineering Group as a portfolio architect, and he's going to cover the Ceph-based solutions. Steve Watt, as I just pointed out, he's a consulting engineer with the Office of Technology. Steve's going to cover the containerized Gluster solution. My name is Sean Murphy. I'm a product manager with the ISBU, and I'm going to talk to you about the Rev and Gluster solution. So let's start with a simple definition of hyperconverged, kind of a standard definition. The industry sort of broadly defines hyperconverged as collapsing storage and compute into a single unit or a single solution as a unit of deployment. And as you see here with this IDC example, and that's fine as far as it goes, but what we're finding in talking with customers is that there's a variety of problem spaces, use cases, a range of use cases that these customers are bringing to us that are driving us to develop sort of solution-aligned offerings in the hyperconverged space. So if we zoom out here just for a sec, tie this back to the broader context, it's all about software-defined infrastructure. And as you know, Red Hat, it's been a long time since we were just considered an operating system vendor that had a few trinkets on the side, right, to get things done. We're an enterprise infrastructure stack provider, and we have a solutions. We look at problems through a solution-aligned lens, effectively. The hyperconverged solutions that we'll show you today they follow that kind of thinking. We know there's no one-size-fits-all or silver bullet for a lot of these solutions, and at the end of the day, we're looking to satisfy customer solutions. Tushar.
Next, we'll take a look at how we got here, a little bit of a historical perspective, right? So what I wanted to show you are these two charts. One on the left is the speed at which they see how the CPU speed or microprocessor speeds have evolved over time. And on the right, you have the spinning media, how they have evolved the speeds. And you can clearly see that there is, you can see the difference between these two graphs right away. The CPU speeds have consistently increased, whereas the disk speeds have kind of started to level off at some point, right? So this has created an imbalance in general, right, between compute and storage performance. And therefore, we have gone from and evolved from direct-attached storage to more centralized storage, and now we are at the distributed storage phase of the industry, right? And we have two leading distributed storage solutions we're going to talk about today. So what does that mean? So even this is a graph of two charts here, just a representative sample of how much time the CPU spends in various states on a storage node, right? This happens to be with performance with Ceph cluster, but I'm sure it is the same with cluster too. And in fact, there was a presentation earlier in the day today in which somebody pointed out from Intel on Ceph, and it had similar things, which is basically if you look at the blue is the idle times, the amount of time the CPU spends in idle state, and the orange is the I/O wait times, the amount of time the CPU spends, waiting for I/O to complete. And if you add them up, it is basically more than 50% of the CPU is basically doing nothing, right? So that's unused capacity that you are not using. So this is the imbalance that I was talking about, the journey between improving that balance between CPU and disks earlier. We need to continue to do that, right? So that's why we are saying that we need to do hyperconvergence so that you can take advantage of the unused capacity. So with that as a kind of a preamble, let me dive into some of the Red Hat hyperconverged solutions that we're going to talk about today. For a traditional virtualized data center, we're going to talk about Red Hat virtualization, Red Hat enterprise virtualization, so virtualization product, popularly known as RHEV, and Red Hat cluster storage. And Sean will talk about that in a little bit. I'm going to talk about Red Hat OpenStack platform, hyperconverged with Red Hat Ceph storage. This is for your private cloud. And then finally, Steve is going to talk about Red Hat OpenShift and cluster for containerized applications as a containerized platform. So what are some of the, what are the things that are tying this together? It is basically the storage solutions from Red Hat, which is Red Hat Ceph and Red Hat cluster storage. So what are the benefits of hyperconvergence? The first one really is you can go from simple. You can start off very simple. You get compute, storage, and networking all in one. So if you're going to kick some tires, be it OpenStack or containers or RHEV or what have you, you get everything in one box, if you will. And so you can start off simple. Then you can kind of scale out, and we'll talk about it, and you can scale out on either the compute axis or the storage axis, or you can on the hyperconverged axis. So you can grow as you need, depending on how you want to do. There are other use cases where you may not want to grow at all, like small footprint. Like there are several use cases such as telco, point of presence, or retail office and branch office, wherein you just the most important commodity there is real estate, and customers want that to be optimized, and therefore you can use it there. That's a target use case. Also what happens is, now we talk about better resource utilization. Since you're using the CPU, unused CPU capacity, and you're also delivering storage out of it, you get better resource utilization. Now let's say we said more than 50% is spent in idle, right? Let's say we have 30% of it across hundreds and thousands of servers and data center. That's a lot of saved capital costs as well as operational costs, right? So there's power, there's real estate, there's cooling, you've got to pay for all that, so that lowers your TCO. And then finally, as with everything, the Red Hat solutions that we're offering and we're going to talk about today, it's based on open source projects. It's all out in the open. In fact, when I talk about the OpenStack and Ceph, we have introduced some scripts and we added some heat templates and so on and so forth. Those are available upstream. You can go and play with it. So basically, it allows you to participate in that and avoid any kind of perceived or real logins. So with that, I'll next talk about Red Hat OpenStack and Ceph. This was a great team effort from a bunch of people at Red Hat, so I want to just mention them here before I go into it. So this is the functional diagram of what it is. It means to be hyperconverged OpenStack and Ceph. As you can see, OpenStack has these services. The key ones really are Keystone, which is an identity service, Glance, which is the image store or image service, Neutron, which is the networking service, Noah, which is the compute service, and Cinder, which is the block service. And Ceph provides, in this case, Cinder, ephemeral, and Glance storage. So that Ceph is the backend store for all these services. And what we're doing here with hyperconvergence is we're saying, okay, the controller basically is going to run all the OSP services and some ancillary services that are required by the Red Hat OpenStack solution, and then it will run Ceph monitors, and then the hyperconverged node is going to run the Nova compute here and the tenant VMs, obviously, or guest VMs, guest simply, and then it will run the Ceph OSPs, and this is where all the storage is, right? So all the disks can be used for that. Then finally, we have something called the OSP Director. I'm assuming many of you know about it, but for those of you who don't, it's a deploy it for the Red Hat OpenStack, and it's based on upstream below. And then you have a Ceph installer, which is an Ansible-based installer, which is also it's called Ceph installer. So you Hyperconverged, you basically run these two things on the same node. So that's essentially the functional diagram. So we did a reference implementation. We set this up in the lab, and this kind of gives you the idea of what that looked like. So starting off with here, we have a controller. As I said, it runs all these services, the OpenStack services, and then it runs the Ceph monitor, and there are three of them, as you can see there, for high availability. Three, basically controllers and Ceph monitors running. And then you have the hyperconversion node, or the data plane, I call it, where then you have the node compute, tenant VMs, and Ceph OSDs, hyperconversion on this node. And then you have another node here, which has the OSP director and the Ceph installer, OSP director and Ceph installer. And so they're connected by some networks. At a high level, basically, you need a network for Ceph traffic, you need a network for VM traffic, and then you need some management and provisioning network. So I won't go into too much detail of that because of the lack of time, but that's approximately what it looks like. And that's specifications of what we use for this setup. So in terms of deployment steps, what are we doing? We're going to take, so what you really need to do is you basically install the OSP director and the Ceph installer on a node. You start with that. And then what you do next is that the OSP director goes in, it drops the hardware, and it then it asks you how many controllers and compute nodes you want to run, and so you can configure that, and then you can deploy. So with that, you get your OSP over cloud running. So those are the three controllers and n number of compute nodes that you wanted to run. And then as a next step, what you do is you ask Ceph installer to go and deploy Ceph monitors on the same nodes where the controllers were installed, and the Ceph OSDs on the same nodes where the end computes were installed. So now you've got controllers running, compute running, no compute running, you've got Ceph monitor running on the same nodes, and you've got Ceph OSDs running on the same nodes. And then finally, you make the connection between the OpenStack, Ceph cluster and OpenStack. Basically, you're telling you configure OpenStack to use Ceph as the backend for Glance and Cinder and Noah as a for everything. So that's the high level what happens. So you get your hyperconverged deployment. Next, what we did was that we ran some performance benchmarks. We basically ran sequential I/O, random I/O, and a small file, and we ran Sysbench, which is a MySQL MariaDB based benchmark. And so I'm not going to go through all of our results, but what we said we'll do is present the best case and worst case here. So, and what you can see here, just in terms of setup, this is on the y-axis the throughput, IOPS, and then on the x-axis is basically number of instances or guests per server, and then we also plotted on this axis there is the in these dotted lines are basically latency response that the guest is experiencing. And as you can see here, as you increase the number of servers, the hyperconverged and non-hyperconverged, we can baseline it against a non-hyperconverged setup, and they track pretty evenly, as you can see here, until they reach a threshold. And after that, those instances, the hyperconverged obviously performance is. I mean, in this case, it is dropping. In this case, it's not dropping. But basically, there's a threshold where then things are not tracking anymore. So I mean, and this is kind of a general pattern that we observe that after a certain, I mean, it's expected, right? Go ahead.
Sorry, in this case, non-HCI. Did you describe that and I missed it, or what is the non-HCI setup?
Non-HCI setup is basically Ceph cluster separately and OpenStack separate.
Okay.
Separate.
Thank you.
What did the tool use? What benchmarks did you use? CPT or?
For sequential I/O, it was IOZone. For random I/O, it was FIO and Sysbench for the most synthetic workload. So anyway, so the main takeaway from this really is that As you can see here, the performance between hyperconverged and non-hyperconverged is not that different until it reaches a certain threshold. And of course, that threshold is going to be definitely dependent on your workload. And so, based on these performances, what we said is we offer some guidance, right? And the guidance really is one of them. Many of you who have talked about hyperconvergence, you know this, right? The main thing really in hyperconvergence fear is that you're trying to run a VM or some kind of a guest, and it might interfere with Ceph, or Ceph might interfere with them. So, so that's what we are trying to allay here by providing some guidance on how to make this work. For memory, we're saying you start off, Ceph needs memory, right? And if it doesn't get memory, it swaps and the performance really tanks. So you want to give it the memory it needs. So it's 3 gig per OSD is kind of where we are at. And then in terms of, so once you you need to take that amount away from NOAA because you don't want NOAA to use it for guest instances. So you do that, here by setting that variable in NOAA.conf. And similarly for CPU, what you do is that for CPU, two things you're trying to prevent is you want to give Ceph what it needs, at the same time you want to give guests what they need, right? So the headroom for Ceph is basically, let's say, 1 port per OSD, and what happens by default, OpenStack overcommits and overcommits CPUs because it thinks that a node can run more instances because they're not going to be fully utilized. So you want to reduce that in this case so that you can allocate it for, you can adjust it for Ceph. And by the way, both of these formulas, there's a little more detail to the formula. I didn't want to go through all that, but we have scripts which are upstream for this. So you could, we have an Ansible, a heap template to orchestrate this one. So the next one really is the Ceph needs to be throttled as well. So one way to throttle Ceph is really to NUMA attach the Ceph to a NUMA socket or a NUMA node. And then, so that way Ceph stays in that boundary. And then the other thing to do is that when use a less aggressive recovery throttling. So when Ceph actually has to recover from failures such as OSD failures, it tries to restore those OSDs, and so it gives a lot of priority. Is what we had observed, that there's a very high priority is given by default in Red Hat's Ceph storage 1.3.2, which we have changed in 2.0, but if you're going to use Red Hat's cluster storage 1.3.2, you don't need to. You need to, and we have an Ansible play for that, which also you can find upstream. Next one is network. You have to have two. What we observed is that you need to give network to be a bottleneck. So for Ceph particularly, so you need to allocate at least 10 gigabyte each for what I would call front end and back end traffic in Ceph. And then you need to obviously allocate some network for the next and for the VM workload. And finally, in terms of storage, for most general purpose storage, what you can use is NVM, non-volatile memory express SSDs for Ceph journal, and then you can use your spinning media for storage, spinning disks. But if you're going to go all intensive, IOPS intensive workload, then you might want to think about all SSDs. And in fact, there's a great presentation, like I mentioned earlier, from Intel earlier about the high performance that they are getting out of Ceph by using all NVMe SSDs. 1.4 million IOPS is what I saw. So anyways, target use cases. For this solution, I said earlier, for NFV, one of the big problems that we had before this was that for your first compute node, you'd have to have a OSP director, and then you'd have to have 3 HA controllers, and then you'd have to have 3 Ceph OSDs, because that's the supported configuration for your first compute node. And so instead of doing that, what we have now done with Hyperconvergence is you can use those 3 Ceph OSDs as compute capacity too. So that's, depending on how you calculate, right, it's about 30% improvement there, right, reduction in footprint size. Similarly, you can use it for enterprise POCs. Also, I mentioned it earlier. You can start off, you get all in one, you get all your services, you get all your core OpenStack services, compute, storage, identity, all in one, and so it's a good way to start off a POC. And then the last thing I want to mention really is that the advantage with this approach is, let's say you start off with that POC, right, with the basic configuration. If you want to just add compute capacity, you can do that. If you want to add storage capacity, you can do that. But if you want to add both of them, depending on your circumstances, you could add a hyperconverged output. So that allows you a lot of flexibility in what you want to do. So those are the target use cases. With that, I will hand it over back to Sean to talk about the next solution.
Okay, great, thank you. So this section will be decidedly less technical, because I'm a decidedly less technical guy than this guy. But we'll give you a high-level overview of what we're doing with the solution with Rev and Gluster. So, broadly speaking, this is like most of the integration efforts that we're doing here at Red Hat across the stack. It's all about the gestalt, right? It's the whole is greater than the sum of its parts. In this particular case, the parts that we're bringing to bear are Rev and Gluster, so Red Hat Enterprise Virtualization and Gluster, which are each very powerful components on their own. They both have a long pedigree together. They're industry proven. There's a level of integration that has existed between them for a number of years now that gives them, a natural affinity to begin with, and we're taking it the extra step to tie in. Optimizing workflows and optimizing, connecting in fault management and correlation and so forth, monitoring, reporting, to deliver a full, nice, tight, integrated, hyperconverged solution. So for probably a couple of years now, and particularly in the last year or so, we've been seeing a fair bit of demand from the field, and we've been seeing both open community people sort of bootlegging this kind of a configuration themselves, either with upstream bits or downstream bits, and even some commercial organizations that have effectively bootstrapped this on their own, right? And they get by with it, but it's really not sufficient because of the other pieces I mentioned, the integration pieces I mentioned a minute ago. And so there's been a lot of pull, as I said, particularly in the past year, and it's much of that outreach has been clustered around these markets, oil and gas, of all places, and retail robo. Now, in the oil and gas case, it's a lot of that is also a remote kind of situation, so it has similar profile to what the retail guys need to do with their remote offices. But there's also central data center interest, and there's always a smattering of test dev around in there, right? But most of what we're looking at right now for what we're getting pulled on is those market spaces. And what do those guys need this for, right? So they need it for the same reasons that we need, we're making changes in the broader data center, right? Managing data growth is not unique to a robo market, so and it's not unique to the central data center. But other, robo markets, remote office, branch office markets are characterized in part by having generally limited IT resources, right? So they're not going to keep hiring 150K sysadmins in these operations as they need to grow data. So removing the discrete storage tier in and of itself starts to deliver value right away. Then there's things like the backup and recovery and DR stuff that they have to do, right? There's a lot of fault. It's a very error-prone process. So adding image-based DR and image-based backup saves them a lot of hassle in that space. And then there's obviously the space and cooling and the deployment issues of having to grow these compute infrastructures in these remote spaces. And some people might argue that why not just run most of the stuff from the central DC and kind of wean these guys off of having to do anything at the remote offices. But the fact is that for performance reasons, and in many cases, regulatory compliance reasons, they need to run in the remote facilities. So how are they doing it today? Well, obviously, in most cases, they're doing it just by doing smaller versions of what they do in the central data center. Excuse me. And as I said, that reaches a threshold pretty quickly where you're building a house of cards, right? They can't manage these things beyond a certain point. Again, removing the discrete storage tier is the biggest savings right off the bat, right? Integrating the storage with the compute and delivering a single pane of glass to manage all of it, it delivers immediate value to these operations. But they have other choices, right? They could either do nothing. That's your house of cards syndrome. They could farm out to MSPs or external IT management operations. But what we're hearing from customers and what's backed up by the analysts that we've been talking to is that that's basically a non-starter for most of these guys, and that's why the bulk of them are looking at hyperconverged. One of the differences here is that while there's a hyperconverged market, there's a bunch of gold-plated solutions there today, and the market really hasn't consolidated yet. It's only a matter of time before that happens, and most of the customers that we're hearing from, they don't need all of the extra bells and whistles, right? It's a product hygiene or table stakes issue that we'll be delivering with this product that will satisfy a lot of these use cases. So, excuse me, from a deployment standpoint, very simple deployment model. These Rev Gluster hyperconverged clusters start as a 3-node pod. That's the initial footprint. From there, they can scale out by one. When we get to the GA version of the product, you'll be able to just start with a single 3-node footprint and expand compute and storage by one node from there. Initially, and I'll talk about this in a minute when we talk about where we're at for availability, solutions will be software-only solutions that will be accompanied by reference architectures. And eventually performance characterizations tied back to those to give customers a fighting chance to find the right gear for their compute and I/O profiles. So what does it all boil down to, right? It boils down to infrastructure consolidation and operational efficiency. This is what these customers need, and this is what they get from this type of solution. Not having to staff up as they grow, not having to buy additional storage gear and have to deal with different management tools, different, the storage networking itself, bringing it all together into a nice tight package, consolidates the infrastructure and by virtue of that delivers operational efficiency. So we have just a ton of these use cases that are laid out like this, a simple A/B thing, right? There's not a lot of technical detail here. You can look at the punchline at the bottom and say, okay, wow, that looks good, right? But I didn't want to come up and drag a bunch of these out in here. I'll just show this one quickly. The customers that we're working with right now, many of them are doing this type of equation on their own, right? They're measuring TCO and they're seeing, they're seeing dollar values that they're really, ring the register for them. So I don't think that there's any confusion right now in this market space that hyperconverged is the right solution. Coming to Red Hat is the value of coming to Red Hat has to do with price performance. It'll have to do with the deeper integration that we'll be able to provide back to their central DC through CloudForms and satellite and things like that no one else can actually touch. So I hinted at this earlier. This is we have a limited availability program for this product, for this solution, and we're targeting availability to a handful of customers, sort of hand-selected customers, in the next month or so. So this will be a controlled release, and it will run for several months as we work toward the GA version of the product. If you want detailed information on that roadmap and the availability, please see me or see your sales rep and we can talk about that. I don't have a slide on that here. But this limited availability program is still open. There's only a few slots left in here. The idea is it's a close engagement kind of relationship, but it's not a beta. It's not a tech preview. This is a fully QE'd product. So stability is there. And we have several customers in these market spaces that are involved in the program. But as I said, there are a couple of other slots if people are interested, would be interested to hear from you. Okay? Thank you. I'll hand over to Steve.
Thanks, Sean. Hi, folks. I'm Steve Watt. I work on Red Hat's container storage initiatives. Support them both from the platform side with OpenShift and Atomic Host, and also on the storage side with Gluster and Ceph. So before we get too far along, I sort of wanted to start with Red Hat's perspective. Red Hat's perspective around persistence with containers and how we got there. So this is sort of, if you look at sort of as you move along towards building a solution, this is a number of different engineering dimensions that you have to consider and a sort of perspective along them, right? So if you start at the development model, right? So each dimension is a column. And the development model, we started with waterfall and moved to agile, and we have DevOps now. Application architecture, we started with sort of single server, monolithic architectures. We then broke that out to 3-tier and then N-tier application, SOAs, and now we have microservices. If you look at the unit of deployment, we started off with sort of bare metal, and then we found out, hey, we could do much better job of utilizing all the resources on the server by actually carving them up and virtualizing them across our data center. So we did that. And then we found out, hey, we can be even more effective at managing those or getting better utilization of our resources if we use containers. And then infrastructure, we started off with a few servers. Those grew into data centers. Some folks experimented with having other people host their data centers. We had the advent of public cloud, private cloud. And so effectively, the cloud, whether it's hybrid, private, public, is sort of our model. Now, if we pause there and just sort of look at storage, storage, we started with scale-up storage and ran out of disk space and capacity. It became increasingly expensive to buy bigger and bigger servers, and so we moved to scale-out storage, with the original proprietary being the original scale-out storage, and then that became open source and software-defined. And then if we pause there and we look at, how well does that fit the rest of the stuff on the bottom row? Well, it doesn't really fit very well, right? So if you look at DevOps and hybrid cloud, right, you say, sort of hybrid cloud, you can provision storage via API, right? And that's great because that fits into the DevOps model where the storage admin gets out of the way of the developer being productive. So, current historical storage solutions, you have to, get a storage administrator, submit a workflow or something to that effect for them to create you a volume or a LUN or something. Takes a couple of days, or at least a few hours before that happens, right? So that's not very DevOps. And so what we ended up doing is sort of looking at that and then saying, look, microservices packaged as containers. Well, when those applications are running, how easy is it for those things to connect to the different storage platforms that you've already bought or are planning to buy? Well, historically that hasn't worked very well. So what we sort of came up with was this sort of point of view that just because you package something as a container doesn't mean that the needs of the application that live inside that container change, right? If you're running a MySQL database, you probably want a place that you trust to store the files for your MySQL database, right? And so, we need to store state, have a good solution for it in a model that sort of supports DevOps, agile processes. Storage has got to be easy to set up, access, consume, and release. And actually, just to sort of show the Red Hat way of sort of approaching these problems, I have all my colleagues sitting here what we did is we actually tried the stuff ourselves, right? So roll back 18 months ago when we first started working on a lot of these things, we started building applications and made lists of the things that drove us nuts or the things that just didn't even exist, right? And then went out to addressing those. And so that is sort of the story I'm going to tell today, right? So the first thing we went out and fixed is the ability to connect your containers to the different storage that you have today, right? Specifically Gluster and Ceph, right? And so if you imagine, you have your OpenShift cluster over here, right, which is our container platform, and you have your storage clusters over here, right, and they're accessible via the network. We went and built out a whole host of volume plugins within Kubernetes, which is exposed up through OpenShift, so effectively storage adapters. And then we also built out the storage subsystem within Kubernetes, right? And so we added things like NFS, iSCSI, Fiber Channel, access to GCE persistent disk, Amazon EBS, Gluster, Ceph, NFS, etc., right? And so we built all of those things out so that people could run containers and have persistence. And this has been GA since November of 2015. There's a lot of FUD out there about containers and persistence. I personally believe a lot of that is not about, is dependent on the container orchestration framework you're using. That is not so much a problem with Kubernetes. That stuff's been baked, and we support this in production for, GA, industrial strength, for a while now. So we provided access to Ceph RBDs and Gluster volumes, and that was November 2015. The next thing that we went and did is we went and we containerized Gluster FS. So, traditionally when you consume Gluster FS, it's an RPM. And so we now offer, container images for Gluster FS. And that has been GA since March 2016. And you're able to obtain those from the Red Hat registry. And so this is really a stepping stone to really get us to what I'm here to talk about today, which is one of our big announcements at this conference, which was the container converged storage, which was actually the ability to run containerized Gluster FS in OpenShift. So once it was containerized, then we could actually basically look at the OpenShift primitives, the replication controllers, and deployment templates that we needed to build to actually be able to run this within OpenShift and work on that and tighten up the security and basically make this usable. And so this solution is very similar to the other two solutions you saw in the past, where it has the sort of same benefits. But if we start off with why would someone consider something like this? Well, when you're deploying a container platform, right, sometimes you don't always have access to the storage that you have already because it's oversubscribed, right? Or it's like the storage systems can be a lot like databases, where you have your database administrator won't allow another application to connect to the database, right? Because it's already oversubscribed, it'll affect the performance, etc., right? Or it doesn't have the capacity to support the persistent needs for the container applications that are running in OpenShift. So, if you, for whatever reason, are running into issues where it's harder to connect your existing storage assets to OpenShift because of some reason through using our network options, there's this option to actually run the storage platform within OpenShift, right? Because there's a long delay, right? You have to submit a capital request, go buy the infrastructure, go set it up, etc. And so you can actually get productive immediately using this approach, providing storage within OpenShift. Now, obviously, within your OpenShift clusters, there needs to be servers with direct attached storage that we can land the containers on to actually, we can't manufacture storage hardware out of thin air. But so those have to be there. But it obviously will lower TCO. But the other thing that's kind of interesting is that it uses the same control plane. So Sean mentioned the issues around finding skills and things like that, right? Well, when you're able to deploy your storage platform using OpenShift, and you're actually using the OpenShift control plane to deploy it and manage your storage, right? So you can actually sort of leverage that existing skill set, right, around OpenShift and Kubernetes, right? So the architecture is quite similar to what Sean just showed as well, where you start off with 3 nodes, right? And then you're able to expand by adding a node at a time from there. And it's Gluster FS running on containers. And what we do is we make sure those Gluster containers land on specific nodes that have direct attached storage. You've got to tell our deployment system exactly which nodes those are so it gets it right. But this is sort of the initial offering. I'm actually going to close with the demo, so I'll demonstrate all of this. But the key enablers to actually do this, obviously the containerization of Gluster, but we leverage the the GlusterFS volume plugin that I demonstrated earlier, the first release of the network storage adapter. So we leverage that to allow your containers to be able to connect to these new volumes that we're providing. And then we've done something pretty cool, which is create a service interface to Gluster. So if you remember on like my very first slide, the point of view slide was like, we need storage as a service, like API-driven provisioning of storage. We've now added that to Gluster through the Hikeri project. So people can just run a command and provision storage via the API. And so if I sort of look at the roadmap, because this is probably the most bleeding edge of the, or cutting edge of the solutions that we've shown today, right? This is an evolving story, right? And we've taken the best of Gluster and of OpenShift to put this all together. But it's an evolving story, and as it continues to evolve, we'll continue to add features to it. And so, I sort of covered the middle slide that will GA this summer. But what's coming next is the ability to actually is dynamic provisioning in OpenShift. And so what that means is a developer can submit a claim, a request for storage, and it'll be a pass-through right the way through to Hiketi, which is our provisioner for Gluster. And so basically, the developer submits a storage, and it will just provision the storage automatically and bind it to their claim and make sure it's available to them to be used that instance, right? So you ask for 100 gig volume via API, it gets made and assigned to the OpenShift developer, and it can be used instantly in their application, right? All the storage coming from the Gluster application running inside OpenShift itself. And deployment usability improvements. So the demo I'm going to be showing you now is terminal-based. As we advance the state of the art within Kubernetes, which is the container orchestrator that underpins OpenShift, we're looking to add a few primitives inside the Kubernetes project that will allow us to make it easier to use the OpenShift console and have a fully GUI-based deployment of this. Right? So those are two key things that we're working on next for the solution. So I'm going to give you a demo and sort of walk you slowly through the demo to sort of give you a sense of this. But before I do that, could I just ask the folks in the audience here, how many folks here are actually running OpenShift right now or have seen it deployed? Okay, so about half the audience, right? So for the other folks that aren't familiar, OpenShift is our container platform. And it's a master worker architecture. So there's a master server that you essentially submit requests to run applications. And then those applications, which are containers, get scheduled on workers, other nodes in your cluster, right? And so when we deploy Gluster, you'll see that it'll be a set of commands. I'll pause and sort of walk you through it so that you're up to speed. So let me just... Okay. Whoops, let me just back this up quickly. So, all right, so the first thing I'm going to show is the OC command. So in OpenShift, basically the CLI is OC, OpenShift command line. And get nodes will basically list the workers that are available in my cluster. So as I mentioned, you start off with a 3-node cluster. So I'm showing 3 nodes, IPs 100, 100, and 102 that are available in my cluster. Then next, I'm actually going to go off and deploy GlusterFS. Okay, so you can see I deploy 100, one to 100, another one on 102, and another one on 101. Now, that was fast. I just deployed a 3-node GlusterFS cluster in about a second. So that's something to pay attention to. Anybody who's ever deployed a storage platform on cluster, that's pretty damn amazing, right? And so that's kind of interesting with containers in general. We're seeing as we're bringing that technology to our storage platforms, there's a huge advancement in that the packaging innovation brings to simplifying deployment. Okay, so I've now got 3 containers running. I'm now going to deploy Hiketi, which is the service interface to Gluster that I mentioned that allows the provisioning of volumes. And the OC get pods is a pod is a unit of deployment within OpenShift, and get pods will show you all the different pods and the status that they are, and you can see it they're running, right? So I've got Hiketi, I've got GlusterFS running, and the router is an artifact of OpenShift. It's not really specific to our solution, but for those that are interested, it allows address translation between our software-defined network in OpenShift and the external network. Okay, so the next thing I'm going to do is list the Hiketi cluster, right? So Hiketi being the service interface for Gluster. I say, hey, Hiketi list, show me what GlusterFS clusters you know about. And it returns nothing because it doesn't actually know any, it hasn't been taught. So the next thing it does that I'm going to do is pass in a topology JSON file where I'll actually teach the cluster about the GlusterFS topology that's been deployed, right? And then I submit it, and then what you can see is it's learning about the cluster, right? So, IP 100 is one node, 101 is another, 102 is another, and all the devices attached to each one, right? So that's obviously laid out inside the topology file. So it knows about that, which is great. And when I do cluster list now it's got a UUID. It knows about a particular cluster, and that's good. But the problem is that we want to store this information in a reliable place, right? So actually we want to store the Hiketi database in a Gluster volume itself because it's got a three-way replication. So what we're going to do is run a set of commands that will move, now that we know about a Gluster database, we're moving the database file into the distributed file system, and then we're restarting Hiketi, and what will happen is when it comes back up, which is what's happening right now, that it's mounted the GlusterFS volume that has its database. So it's basically, we bring Hiketi up, we teach it about Gluster, and then it uses that to create a small volume, store its database on there, come back up, mount the volume, and from thereafter it will always use that volume for persisting its information about the Gluster files and, the Gluster cluster and where all the different devices are that it needs to know, because Hiketi has got some pretty amazing math inside. Every time you ask it to create a volume, it will look at all the different devices and make intelligent decisions around how to create bricks to provision the volume. Okay, so at this point, we're done, right? It's deployed and running, right? So the next thing that we're going to do is we're going to set the RESTful server, the Hiketi RESTful server DNS as an environment variable, and we're going to start creating volumes. Okay, so that's what that command is, export Hiketi CLI. I'm now going to start using the command line interface to start provisioning Gluster volumes. So Hiketi CLI, and then you'll see the cluster list, right? So it knows which cluster to provision from. You can change that, obviously. And now we're going to create a 100 gig volume, and we're going to pass in this -- persistent volume command, and that tells Hiketi to actually not only create the volume, but register it in OpenShift automatically for you, right? And you'll see it's pretty quick, right? Okay, so what happened just there, 100 gigabyte GlusterFS volume was created out of our Gluster cluster running inside OpenShift. And not only that, but it created an OpenShift persistent volume, which is basically like a pointer to the GlusterFS volume. And that means that there's now a volume in the OpenShift pool that a developer can claim and consume, right? So if you're not familiar with OpenShift persistent volumes and how they work, just a quick digression because this will probably help you. The way OpenShift works is that you have a storage pool, and you can add things called persistent volumes to this thing. Each persistent volume is a unique storage resource that a developer can claim and own. And then when they're done with it, they can release it and it'll go back to the pool, right? And so what we've done is, and the the persistent volumes are obviously just pointers to real-world storage resources that live somewhere, right? But contain all the information that OpenShift uses to actually mount that thing, right? It's more like another example, yes, sort of. But it's more like an ODBC object, right? So like, if you remember, ODBC connections had all the information that you use to connect to the database, but all they are is just a pointer with information. That's what persistent volumes are, right? It's pointing to a storage resource rather than a database. Okay, so it's created, and now what's kind of cool about this, or what's very cool about it, is the way we expose the networking. These Gluster volumes can be used by the OpenShift applications, but they can also be consumed by applications that are outside the network, right? And so what we're doing is we're going to mount the volume, and we're going to create a little file in it, a little index.html file that we're going to submit an OpenShift application that will mount that and serve that, right? But you're going to see us mount the volume now. So this basically shows the persistent volume in the pool that I mentioned, right? This command will demonstrate the actual volume name. So we use that to basically mount the volume. So we're going to pass in that volume name here in the mount command. So we're going to directly mount the volume. So this sort of shows the use case of being outside of OpenShift and still using it, but it's really more just anecdotal, just to create a file. So you can see the mount command work there, the bottom of the screen. That's the Gluster volume. Now we're going to just create a little index.html file. I love GlusterFS. And then once that is added to the index.html, we'll unmount the volume, be done with it, and then I need to get ready to pause here because you're about to see a lot of OpenShift info, right? So, okay, here we go. All right, so in OpenShift, when you submit an app, right, apps run as containers. They can be scheduled anywhere in the cluster. And so you can create these things called services, which create a consistent known endpoint for that app. As it gets moved around the cluster, the IP will always be the same. So that's what the service is over there. And the route is a part of that. It allows the service to be addressed outside the cluster. And then as we scroll down, the next thing here is the persistent volume claim. So you can put all of this inside one file, or you could submit those as individual files in OpenShift if you wanted. The purpose of the demo, we just put it in one. But this persistent volume claim is what a developer would submit. Say, hey, give me one of those persistent volumes in that pool in your cluster, right? So I'm asking for a 100 gigabyte piece of storage, right? And what's going to happen is it's going to bind to the one that I created out of the cluster. The next thing, the pod, is the actual app itself, right? And so what the pod is you can see it's an Nginx application. So it's going to launch an Nginx web server, right? And you don't have to know too much about the mount part, but if you look at the mount parts, what it's doing is it's taking the volume that gets mounted into the container and mounting it into a particular directory in the Nginx container, which is user share Nginx HTML. That's the document root for Nginx. So whatever gets mounted, it'll start serving straight from that. So this web server is going to mount the volume that we just created. So that gets submitted, which is what this stage is here. And you'll see all the different assets that got created there, right? The service, the router, the volume claim, and the pod being the app. And we're just going to see there that the claim status. If you see at the bottom there, the status is bound, which means that the claim was submitted and it was bound to the persistent volume GlusterFS-87 ... which was the one that we created using our deployment technology. Now, this bit is the curl, the big test, which is now that we curled the URL from Nginx, and it says, I love GlusterFS, right? So just to reiterate, so the demo that I've showed, we deployed Gluster, then we used the Heketi client for the RESTful interface to create a volume and automatically register it inside OpenShift. We then found out that volume information and manually mounted it from outside the cluster created a little index.html inside the volume, unmounted it, and then submitted a claim for to bind that volume, passed that claim into an app, and the app mounted that claim, whatever was in that claim, inside the document root of Nginx, and it is web serving from that directory, index.html, I love cluster.fs. So that's sort of an end-to-end demo. The deployment piece, we're hoping to swiftly move into the OpenShift console, so you don't have to use the terminal, right? It'll make it a little easier to delineate what is a aspect of the administrator versus the developer. So bringing it all back together, we've got 3 different hyperconverged solutions. Red Hat OpenStack and Ceph for your private cloud, Red Hat Virtualization and Gluster for traditionalized virtual data centers, and Red Hat OpenShift and Gluster for container converged storage. We did have a sign that says come talk to us at the booth, but since we're the last session of the conference, that's not possible. We do have quite a few Red Hatters that work on different aspects of this here today, so if you're interested, you can come up front or hang out with us afterwards, or contact your Red Hat rep, or shoot us an email, which those are our email addresses if you want to. But that's the end of our presentation, so thank you all for attending.